Our next lesson is about coordinate proofs for quadrilaterals. This aligns with the CCRSM standard GPE4, where we use coordinates to prove simple geometric theorems algebraically. Now, there are a few problems on the PARCC assessment that are like these, and there is nothing like this in EngageNY. So I wanted to add in an extra lesson right here to go over how to do these kinds of proofs. Now, we're not going to be in EngageNY, so I'd invite you to get a piece of paper, whether it's notebook paper or white computer paper, hole punch it, and put it after lesson 8 and before lesson 9. That's exactly where it'll go in kind of our sequence of lessons. But please draw these diagrams in your notes and also write down these things, and please put them with your student materials so you have them. The first kind of question we'll look at is where you're given a shape, like you're given a quadrilateral, and you have to use the properties of that quadrilateral to define the coordinates of other points using no new variables. Okay, so for example, this is a rectangle, and you're given this coordinate to be AB, and this coordinate is CD. So the question we ask ourselves is, what is coordinate T? Well, I'd have to go over in the x direction this far, which is the exact same as variable c. So the x coordinate of t is c. And then I would need to go up this height of y, which is the exact same y of this point. So CB is that point. Similarly, for point S, to get to point S, I need to go this far in the x direction, which is the exact same as A. And so the x coordinate of S is point A. And I would need to go up this height, which is the exact same y coordinate as D. And so S is AD. So that's an example of the type of question where you have to use the variables that are there to define new coordinates. One more example of that type of question is with this parallelogram. Give the coordinates of point U without using any new variables. So I'm trying to find this coordinate. Now I've gone over this far, and there's no other variables to use. Okay, well, let's think what I have to work with. I can go this far with C, which, by the way, is that far in the horizontal direction. Now, I need to figure out how to define this extra length that, is in addition to C. And the truth is, it's the exact same as A. So this length right here is A, and so if I go distance C plus A, that's the x coordinate of point U. So I'll go in alphabetical order, A plus C, and that is the x coordinate. In the y coordinate, I need to go up this height, which is the same as the y height here. So B is the y coordinate of point U. The other kind of question we'll see is questions where we verify that a certain quadrilateral is what it says it is, or we verify some property about quadrilaterals. So in this one, we are given an isosceles trapezoid, and they've already defined the coordinates for us. We're now supposed to use these coordinates to verify that the diagonals are the same length. That's one property of isosceles trapezoids. So I'll find diagonal LN and diagonal MO and verify that they are the same length. I'll start off with diagonal LN. Now the way that I figure out length is using the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. Now I'm going to call this x1 and y1, and this x2 and y2. So plugging things in, x2 is c, x1 is a squared, plus y2 is 0, y1 is b. So simplifying a little bit, I get the quantity c minus a squared plus. Now 0 minus b is negative b. And negative b squared is negative b times negative b, which is positive b squared. Okay, so just keep in mind that that is what ln is equal to. Next, let's find the length of MO. MO also uses the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. Now I'm going to call this one x1, y1, and this x2, y2. So plugging those in, I have c minus a minus, because that's x2, minus x sub 1, which is 0. And y2 is b minus y sub 1 is 0 squared. Simplifying a little bit, c minus a minus 0 is the same as c minus a squared, plus b minus 0 is just b squared. So you'll notice that these are the same length. And that's it. Okay? One more question like that. Is the figure shown below a parallelogram? Why or why not? Use the given information to justify your answer. Well, we've defined a parallelogram to be a quadrilateral with two pairs of parallel sides. So I'll need to look at the slopes. Okay? The slope of this side is y2 minus y1 over x2 minus x1. Okay? Now, I'm going to call this x1, y1, and this one x2, y2. If I do that, then I get, let's see here, b minus 0 divided by a plus c minus c. b minus 0 is b, and a plus c minus c, these cancel out, and I'm left with b over a, which is the slope of that segment. Next, I will do this other one, which hopefully is the same because it's parallel to it, but we'll see. The slope is, again, y2 minus y1 over x2 minus x1. And I'm going to call this x1, y1, and this x2, y2. So plugging things in, I'm going to get b minus 0. That sounds very familiar. And on the top, I have a minus 0. Oh, so just minusing 0, b minus 0 is b, and a minus 0 is a, and so I get the same thing. All right, so down here, this segment, let me use a different color. This segment down here has a slope of 0. Okay, if you want to see that by plugging numbers in, you get, you define this one to be x1, y1, and I get 0 minus 0 over c minus 0, which is 0 over c, which is 0. Okay, and the top as well is going to have a slope of 0 because if you want to see numbers plugged in, let's see, I'll call this one x1 and y1. So if I plug numbers in, I get b minus b over a plus c minus a. So again, I get 0 over, let's see here, b minus b is 0, a plus c minus a, the a's cancel, and I get 0 over c, which is 0. So I've just verified, let me just point out the fact that these are the same. Same. So I verified, I wish I had more space to make this a little clearer, but looking at the slopes, we see that two sides have the same slope of b over a, and the other two sides have slopes that are both 0, that they're the same. So this video is about coordinate proofs for quadrilaterals. Thank you so much for watching.